All right, let's work through this now. We're doing kind of a strange example here at the beginning of class today. The goal was just to broaden your horizons about the fact that there are plenty of other examples that the book doesn't even talk about, but are important. And this is an example of what's called a Boolean ring. And Boolean rings are, for example, important in computer science applications. We're just considering a set of objects, A, B, and C. A, B, and C are not necessarily ring elements. They're letters here. They could have been colors. They could have been people. We can create something called the power set of S, that is the set of all subsets of S itself, including the empty set and including the entire set S itself. And if you've got a 3-element set, the power set has 2 to the third or 8 elements in it. P of S has 8 elements. Our goal is to make P of S, this power set, a ring if we define addition and multiplication appropriately. And the standard way to do this is what you see here. To define addition of 2 sets A and B in the power set, they're in the power set, to be the union of 2 set differences, A minus B and B minus A. A minus B in this visual here is what's shaded in green, everything in A that's not in B. B minus A is over here in purple, everything in B that's not in A. We're taking the union of those 2 things, so this sum of A and B consists of everything that's colored either green or purple. The product of A and B is defined to be A intersect B, and the claim is this makes P of S a commutative ring with unity. We want to see that. We want to try some examples. Now, we're not proving that, certainly. For one thing, it's actually kind of tricky to try to prove associativity, believe it or not, in this kind of situation. As proving associativity both of the addition and the multiplication, it's kind of tricky. We're skirting that under the rug, but it can be shown. We're focused on things that are a little easier. Find the additive identity, find the unity, go ahead and add a couple of elements and multiply those same elements and square an element and find an additive inverse. Takes a little bit of experimentation, perhaps. Somebody think they found the additive identity and you feel pretty confident? The notation is even suggestive, though that's just an accident. What thing is the additive identity? Nobody had a guess you feel confident in?
Yeah, so.
The empty set is. The empty set is the additive identity. Why? According to this definition, A plus the empty set would be the union of A minus the empty set with the empty set minus A. A minus the empty set is everything in A that's not in the empty set. Well, that's A, right? Because nothing is in the empty set. So everything that's in A that's not in the empty set is everything in A. And the empty set minus A, everything in the empty set that's not in A. But there's nothing in the empty set. So that's the empty set. Maybe that was the part that was most confusing. And that's A. And it's commutative. I could switch it around. Addition is always commutative in rings. What about the unity? I said there were some partial unities, but there's only one full unity. What's the one? By symmetry, you almost have to guess either the empty set or the entire set, right? Because why would it possibly be one of those? Because the symbols A, B, and C are just arbitrary anyway. So I hope that inspired you to guess either empty set or S. Which one is it? S, yeah. A times S, according to this definition of multiplication, is A intersect S, but A is a subset of S, and therefore the intersection of A with S is A. Since A is a subset of S for any, I'm talking about any A in this power set. What's the sum? This set plus that set. I have to go back up to the definition of the sum. Think of this as the A and this is the B. What's in A but not in B? Just one. What's in B but not in A? Just 3. This has got to be 1, 3. Make sense? Just go back up to the definition. What's the product? According to this, it's the intersection. Hey, that's just 2. Is it a coincidence that the union of these is all of S? Maybe, maybe not. They'll let you think about that. Maybe it's a coincidence, maybe it's not. What's 1, 2 squared? I have to intersect 1, 2 with itself. In other words, it's 1, 2. And that's going to be the case for every element of the power set. A squared will equal A for all A in the power set of S. In other words, this is a Boolean ring. And it's not as trivial as Z2 is. According to number 50 in chapter 12, a Boolean ring is a ring for which A squared equals A for all A in the ring. When you're not exposed to examples like this, you might think that Z2 is the only example of a Boolean ring, and that seems hardly worth giving a special name to. But this is an example of, in fact, an 8-element Boolean ring. What's the additive inverse of 1, 2? What should I add to 1, 2 to get the empty set? Well, since I'm taking the union of 2 sets, the only way I'm going to get the empty set in a union is if they're both the empty set. So what can I put for B there so that both of these are the empty set? Put 1, 2 itself. 1, 2 is its own additive inverse. As a group under just the addition operation, if you ignore the multiplication, this is going to be abelian for one thing, and isomorphic to the, well, every non-identity element has order 2, isomorphic to Z2, external direct product with Z2 again. As a group, under addition, P of S is isomorphic to this. Because it's abelian, and it's got 8 elements, it's got to be isomorphic either to Z8 or the external direct product of Z4 with Z2, or this one. And every non-identity element has order 2 under addition, so because they're all their own inverses, additive inverses, and therefore it's got to be this one as a group. I'm ignoring the multiplication. You might wonder, is it a field? Is this ring a field? I'll let you think about that. Okay. I would encourage you to think about it. It's just to broaden your horizons here, but I'm showing it to you. I'm not completely ruling it out to understand the basics of this for the test, for example. Next Friday is the test, by the way. So it's worth thinking about some more. Maybe going ahead and trying to see if you can figure out if it's a field or not. All right, for the main part of what we're doing today, I'd like to focus on what is our main goal here for the remainder of the semester. And that's rings of polynomials and ultimately factoring them, understanding how to see how the roots of polynomials are related to each other, for example. And that does involve getting into the weeds a lot on, well, rings of polynomials, especially when the coefficients are from a field. And also thinking about, let me just give you a little picture here. Thinking about ring automorphisms when you're in a situation where you've got one field inside of another. Imagine you've got a field here. So F is a field that's, again, that's a commutative ring with unity in which every non-zero element is a unit, has a multiplicative inverse. after the exam, we're going to be thinking a lot about what are called field extensions. A bigger field that contains F. Which feels a little strange because so far with groups and rings, we've started with the big group, and to understand the big group, we've tried to understand smaller groups inside of them, or smaller rings inside of them, subgroups and subrings, especially normal subgroups and ideals. But when we get into field theory, and when we think about trying to understand factoring solutions of polynomial equations and stuff, it's more natural to think about what are called field extensions, bigger fields that contain the original one. E is a field extension of F. And what we're ultimately going to be interested in the last week of class, besides getting ready for the final exam, is we will be interested in the automorphisms, the ring automorphisms. I could also call them field automorphisms. Of E that do what's called fix F. This is just a picture of where we're going, okay? This will make more sense once we get into those weeds after this next exam on Friday of next week. Ring automorphisms or field automorphisms, because E and F are fields. Remember, fields are just special rings. Automorphisms from E to itself. They're isomorphisms from E to itself that fix all the elements of F. That means every element in F gets mapped to itself under the automorphism, is what that means. When every element of F gets mapped to itself. This is going to help us construct something called the Galois group. And we're ultimately going to use group theory to understand it all. This is going to lead to something called the Galois, and you spell Galois in a strange way. It's French. Don't say Galois. Say Galois group. Of the field extension E over F. I know this doesn't really make much sense now, but I wanted to give you just a little inkling to be prepared when we get there. The theory in this stuff, it's really up there, but I do want to focus a lot on examples. Okay, the theory is going to be much more understandable if you focus on examples. So that's the picture of what's to come. What do we want to do for the rest of the day today? Get some practice thinking about polynomial rings, emphasizing some of the ideas, especially in chapters 16, 17, and well, 16 and 17 mostly. Okay. So why don't we go ahead and look at, I think a good way to start thinking about this is go ahead and look at some practice problems here. One fundamental tool that I've emphasized is long division. That's something that's going to be useful. Let's go ahead and look at number 9 here. This is in chapter 16. Let f of x be this polynomial and g of x be this polynomial in Z7x. Remember, this notation is referring to the ring of all polynomials whose coefficients are in Z7. 7 is a prime, so Z7 is a field, but this polynomial ring itself is not a field. I mentioned that. I emphasized that on Monday. Polynomial rings are never fields. Any element with a degree higher than 1 won't, well, even degree higher than 0 won't have a multiplicative inverse. All right, let's go ahead and follow the directions. Let's go ahead and determine the quotient and remainder upon dividing f of x by g of x. We want to do some calculations to make things concrete. So f of x is 5x to the fourth plus 3x cubed plus 1. And g of x is 3x squared plus 2x plus 1. And I am thinking of these as being elements in z7x. Of course, I could think of them as being elements in z8x or z9x or whatever. Even z6x. Even z5x if I replace the 5 with a 0. We're doing mod 5 arithmetic, but we're going to do mod 7 arithmetic. We want to divide f of x by g of x, find the quotient and remainder. Okay, let's go ahead and do some polynomial long division here. And you do have to use long division in this case instead of synthetic division because we are using, well, we're dividing by a quadratic instead of a linear. So I'm dividing f of x by g of x. So I put the g of x over there. I put the f of x over here. Then ask, what do I need to multiply 3x squared by to get 5x to the fourth? The answer is not 5/3 x squared, because 5/3 is not in Z7. Though we could think of it as the coefficient as being 5 times 3 to the negative 1 in Z7, where 3 to the negative 1 is the multiplicative inverse of 3 in Z7. What is that multiplicative inverse? Do some experimentation. What can I multiply 3 by to get 1 when I do mod by 7? 5. 3 times 5 is 15. Mod 7 is 1. The inverse of 3 is 5. 5 times 5 is 25. Mod 7 is 4. This is all mod 7. So what goes here then is 4x squared. I need to multiply 3x squared by 4x squared to get 5x to the fourth. Right? 3 times 4 is 12. 12 mod 7 is 5. X squared times x squared is x to the fourth. Remember, we only mod the coefficients, we don't mod the powers. The degrees of these polynomials could be arbitrarily high. Million degree, billion degree, etc. Of course, we never actually do examples like that because it would be just too unpleasant, but in theory, that's possible. Now the next step is to multiply 4x squared by each term here and put it down there and then subtract. 4x squared times 3x squared is 5x to the fourth. So those are going to cancel. 4x squared times 2x is 8x cubed. 8 mod 7 is 1. Right? 2 times 4 is 8. 8 mod 7 is 1. 4x squared times 1 is 4x squared. Now subtract. Those cancel. 3 minus 1 is 2, even mod 7. So we get a 2x cubed. 0x squared minus 4x squared. What's the additive inverse of 4 mod 7? Well, add 7 to it. It's 3. Additive inverse there. 3 plus 4 is 7. Mod 7 is 0. 0 minus 4 is 3. Isn't that great? Show your parents. Hey, mom and dad, 0 minus 4 is 3. Could have said that earlier in the semester. Next step, what do I have to multiply 3x squared by to get 2x cubed? well, there will be a factor of x. It technically will be 2 times 3 to the multiplicative inverse of 3, right? Yep. And we've already seen the multiplicative inverse of 3 is 5. Mod 7 is 3. So, yeah, 3 times 3 is 9. Mod 7 is 2. This is going to be 3x. Now multiply it times each term. Again, 3 times 3 is 9. Mod 7 is 2. X squared times x is x cubed. 3x times 2x is 6x. Mod 7 is still 6x. X squared, excuse me. And 3x times 1 is 3x. Subtract. 3 minus 6 mod 7. Well, 3 minus 6 is -3. -3 mod 7 is 4. -3 plus 7. 0 minus 3 is -3. Mod 7 is another 4. And then don't forget to bring the 1 down as well. That would be a common mistake, is to forget to do that. 1 minus 0. What do I have to multiply 3x squared by to get 4x squared? A constant. It would be 4 times 3 to the -1, 4 times 5, 20, or that would be 6 mod 7. Looks like we should get a plus 6 here. Six times 3 is 18. 18 mod 7 is 4. 6 times 2x would be 12x. Mod 7 for the coefficient would give you 5x. 6 times 1 is 6. Subtract. 4x minus 5x is -x. Mod 7, that's the same as 6x. 1 minus 6 is -5. Mod 7 is +2. So if I've not made any mistakes here, there's your Q of x, your quotient, and here is your R of x, your remainder. Let's check it. We want to check that when we take G of x times Q of x plus R of x, that we ultimately get f of x. Right? F of x can be written as what we're dividing by times the quotient plus the remainder. That's what we hope. Do all the calculations mod 7. There's no FOIL to do here because you got trinomials instead of binomials. What I do is I go to the first term there and multiply it times every term here. 3x squared times 4x squared is 12x squared, x to the 4th, excuse me. 12 mod 7 is 5. 3x squared times 3x is 9x cubed. 9 mod 7 is 2. 3x squared times 6 is 18x squared. 18 mod 7 is 4. Now go to the next term on the left, this one, the 2x right here. Multiply it times every term on the right. I'm going to put the answer on a line below so that I can see what the like terms are going to be. 2x times 4x squared is 8x cubed. 8 mod 7 is 1. Put an x cubed here. 2x times 3x is 6x squared. 6 mod 7 is still 6. This is 6x squared. And then 2x times 6 is 12x. 12 mod 7 is 5. Finally, go to the 1 here and multiply it times every term. That's nice and easy. And then don't forget to add the remainder as well. Add all this stuff up. Mod by 7 for the coefficients. We got 5x to the 4th plus 3x cubed plus, look at the x squared terms, 4 plus 6 plus 4 is 14. 14 mod 7 is 0. I'll go ahead and write as 0x squared, which is okay to do. X terms is 5 plus 3 plus 6 is 14. 14 mod 7 is still 0. And then we got plus 8. 8 mod 7 is 1. 5x to the 4th plus 3x cubed plus 1. 5x to the 4th plus 3x cubed plus 1. It worked. Fun, fun, fun. Kind of fun, I think. Since the remainder is non-zero, g of x does not divide f of x in this ring. Since r of x is non-zero, g of x does not divide f of x in z7x. It might in some other polynomial ring. You always have to specify what the polynomial ring is that you're talking about. I mean, probably it won't if you picked one at random, but you can't rule it out. It's possible g of x could divide f of x in, say, z11x. What's that? Not divides there, by the way. It's not clear. It's not a big X. Okay. Not divides. Does not divide. Part of my point here is we can do divisibility theory with polynomials, just like we could with numbers. And there's a division algorithm. What does the division algorithm say? Let f be a field. I'm saying mostly we're working with the coefficients being in a field, not always. The next most common coefficients would be z, which is not a field, the integers. But when we do the theory of this chapter, certainly we're thinking about f being a field. Fields are integral domains, and one nice thing about that is that does mean this is going to be also an integral domain, this ring of polynomials. But it's never a field, even if f is a field. F is a field, but not fx. Any polynomial with degree bigger than 0 won't have a multiplicative inverse, won't be a unit. The non-zero constant polynomials will be units if f is a field, right? Because those non-zero constant polynomials, thinking of them as being elements of f, which you are free to do, would have multiplicative inverses in f because f is a field. And therefore the corresponding non-constant, well, constant polynomial that's non-zero constant polynomial would be a unit in here. But yeah, once you get to degree 1 or higher, then it's no longer going to be a unit. F of x is being divided by g of x here. We don't want to divide by 0. The conclusion is there exists unique. The uniqueness is important. You get a unique answer. Polynomials q of x and r of x, a quotient and a remainder in this polynomial ring that will be an integral domain. No zero divisors. Such that f of x is written as g of x times q of x plus r of x, just like we did. We checked. G of x times q of x plus r of x equals f of x. And either r of x is the 0 polynomial, or the degree of r of x is less than the degree of g of x, which is what we're dividing by. We were dividing by g of x here. That was quadratic, second degree. It was guaranteed that r of x would either be 0 or have a degree less than 2, meaning degree 1. Could have been a constant, degree 0. If it was 0 again, 0 technically doesn't have a degree. I'm not quite to the point where I can explain why. It's a technicality. So that's the division algorithm. Generalizes the one for integers. Its corollaries are pretty important to know as well. Corollary one's called the remainder theorem. Let F be a field so that we can apply the division algorithm. Let A be an element of F, which also could be thought of as a constant polynomial in Fx. Let f of x be a polynomial in there. It's got coefficients from f. Then f of a is the remainder in division of f of x by x minus a. Is that hard to prove? It's not too hard. It might not be real clear what to do, but it's not too hard to do. So again, we're looking at this one. I'm not going to do a full proof for sake of time, but it's not too long. Why does this happen? Well, remember, by the division algorithm, if I divide f of x by a g of x, I'm going to get a quotient, a q of x, and a remainder, r of x. And I'll be able to write f of x as g of x times q of x plus r of x. But wait a minute. I want to divide f of x by a special polynomial in this corollary, just x minus a. That's the g of x. The division algorithm, dA, is going to imply f of x is x minus a times some g of x, times, again. F of x is x minus a times a quotient q of x plus a remainder r of x. And we're dividing by a degree 1 polynomial here. That's the g of x. Degree of g of x is 1. Therefore, we also know from the division algorithm that r of x is either the 0 polynomial or has a degree less than g of x, which would be less than 1. In other words, oops, that's supposed to be a g of x. In other words, r of x either way has to be a constant. May or may not be 0, but it's got to be a constant. Call it, say, C. For some C in the field. Or you could think of it as a field element, or you could think of it as a constant polynomial. Either way is okay. And now if you go ahead and you replace x by a, you get f of a equals a minus a times q of a plus r of a, but r of a is the constant c. And hey, that's 0, so this whole thing's 0, and you get that f of a equals c, which, just like this remainder theorem says, is the remainder that you get when you divide f of x by x minus a. F of a is that remainder. So that's the idea of the proof without writing sentences. A related corollary, something called the factor theorem. Once again, the coefficients are in a field. F of x is an arbitrary polynomial in that polynomial ring. That is an integral domain, but not a field. Then a is a 0, a root of f of x, if and only if x minus a is a factor of f of x. In other words, if and only if, when we divide f of x by x minus a, we get a remainder of 0. Oh, yeah, that's a trivial consequence, actually, of corollary 1. Because the remainder is going to be f of a, and if the remainder is 0, that means a is a 0 of f of x. Say that too fast? Too early in the morning. A is a 0 of f of x, if and only if x minus a is a factor of f of x. Thinking about the case where x minus a is a factor of f of x, that means this remainder will be 0, but corollary 1 says that's the function value at a. So a has to be a 0, a root of this polynomial f of x. And it's an if and only if. It works the other way too. If a is a 0 of f of x, then x minus a will be a factor of f of x. I mean, that's stuff you actually already knew from 9th, 10th, 11th grade, whatever, about factoring. You weren't thinking about field theory when you did that. You were thinking just about factoring polynomials when you first learned about factoring polynomials. Corollary, or I guess it's not a corollary. Theorem 16.3 says a polynomial of degree n over a field has at most n zeros, counting multiplicity. A root, say, called the root a, has multiplicity, say, 5, if x minus a to the 5th power is a factor, but x minus a to the 6th power is not a factor of f of x. That would mean a has multiplicity 5 if that happened. It would be a root of multiplicity 5. I'm just verbally saying it here without writing it out. If x minus a to the 5th power was a factor of f of x, but x minus a to the 6th power was not. Yeah, if your coefficients come from a field and the degree of f of x is n, it's got at most n zeros. Can't have more. If the coefficients come from an integral domain, for example, that's not a field, then this is not necessarily true for that example, if the coefficients don't come from a field. By the way, I did notice in reading this, there's a couple typos here. In both cases, right below the proof of this should be saying theorem 16.3, because that's what this one is, not 16.4. You can see it should be pretty intuitive that these are fundamental facts to know about factoring and roots of polynomials. In chapter 17, you get into more details about that. I'm going to come back to chapter 16 here in a minute, but let me just hint at some things in chapter 17. Chapter 17 is about factorization, using definitions of irreducibility and reducibility of a polynomial over some ring of polynomials, where the coefficients come from D, that in general could just be an integral domain and not a field. But we are most interested in the case where D is a field. This definition is pretty hard to understand, I think. Let me just spend a minute giving you the basic idea of it. More important is actually the paragraph that comes afterwards. We won't actually use this definition as is so much. Basically, what you're after here is you're trying to generalize the idea of a prime number, big picture wise. You're trying to generalize the idea of a prime number and prime factorization to rings of polynomials, most typically when the coefficients come from a field. And so in this definition of irreducibility, it is meant to be kind of analogous to the definition of a prime number. It says f of x is irreducible over D if whenever f of x is expressed as a product of elements from D of x, one or the other one of those, g of x or h of x, must be a unit in D of x. In other words, it must have a multiplicative inverse. That's analogous to the fact that when you factor a prime number in Z, like say the number 7, you can only do it as 7 times 1 or -7 times -1. Either way, 1 and -1 are units. They are the only elements of Z that have multiplicative inverses. analogous to either g of x or h of x being a unit in here. That's the motivation for this strange definition. But again, the paragraph below it is even more important, because again, mostly we think about coefficients from a field. Mostly, not always, but mostly. If the integral domain D is actually a field F, this definition is equivalent to this. This polynomial in this polynomial ring is going to be irreducible. They really should have said over F. You always want to emphasize what the coefficients come from. If f of x cannot be expressed as a product of two polynomials of the lower degree. Basic example. Would be x squared minus 2, say, in, I could write z of x. I'm going to write q of x since q is a field. This is irreducible over q because you can't factor it as a product of two lower degree polynomials. You could do a strange factorization. You could, for example, do x squared minus 2 equals, oh, how about 2 times, in parentheses, 1/2 x squared minus 1. You could write that, but that seems silly for one thing. And for another thing, yeah, these don't both have lower degree than the original. You can't factor this as a product of two linear polynomials with coefficients in q because its roots, its zeros are plus or minus square root of 2, and square root of 2 is not a rational number. X squared minus 2 thought of as an element of Rx is reducible over R. Same polynomial, thought of differently. It's irreducible over Q, but reducible over R. Why? R is a field. You can factor x squared minus 2 as the product of two lower degree polynomials with coefficients in R, x minus root 2 and x plus root 2. That's just a little peek of where we're heading. Pretty soon, chapter 7 is going to be pretty important for us. There are a bunch of tests in this for reducibility or irreducibility, especially over field. Though sometimes you are thinking about the polynomial initially say in zx, but ultimately saying it's irreducible over q, for example. Let's end class by looking back at chapter 16 again and look at the reading for the last page and a half, starting with this definition. P.I.D, principal ideal domain. What is a principal ideal domain? It's an integral domain in which every ideal is a principal ideal. Kind of analogous to a cyclic group, right? Every subgroup of a cyclic group is cyclic. Here we're saying every ideal in a principal ideal domain is a principal ideal. It's generated by an element. You can write it as all possible products R times A, where R is from the ring overall. R varies over the entire ring. As an example of a principal ideal domain, Z is, for example. Every ideal in Z is a principal ideal. It's of that form. every ideal in Z, I guess I'm not really proving this, you're just trusting me, is of this form. In other words, it's a principal ideal for some integer n. That's enough according to this definition, if you believe this is true, and you're just trusting me here, that's enough to say that Z is a principal ideal domain, P.I.D. Again, the underlying goal here is just as cyclic groups are the simplest kinds of groups, they help us think about more complicated kinds of groups. Analogously, principal ideal domains are the simplest kinds of rings. They're analogous to cyclic groups. Not only is Z a PID, but also f of x. In other words, the polynomial ring with coefficients from f, when f is a field, is a principal ideal domain. If the coefficients are not from a field, it's not necessarily a principal ideal domain. I think there was one example of that. Not where it was. Must have been in the section about principal ideal domains, chapter 14. I don't remember where it is. I'll look for it maybe after class and see if I can find it. This theorem is where a lot of this stuff comes together, though it may not be clear why. Suppose you're talking about a field and a non-zero ideal in this polynomial ring. I think maybe I mentioned once, fields only have trivial ideals, meaning just zero by itself or the entire field are the only two possible ideals of the field. There are never any non-trivial proper ideals for a field. Why? It's related to what we talked about, I think, last Friday, where we said we proved that if, maybe it was last Wednesday, we proved that if the unity 1 is in an ideal, that means the ideal has to be the entire ring. Remember that? It was a homework practice problem. We went over it in class. So f doesn't have any non-trivial proper ideals, but fx does, because that's not a field. It is, by this theorem, a principal ideal domain. So every ideal in fx is a principal ideal. Let g of x be an element of in this polynomial ring, then I equals the ideal generated by g of x if and only if g of x is a non-zero polynomial of minimum degree in I. Emphasis on the word minimum degree. So if you've got an ideal in this ring, which you know is a principal ideal domain, and you want to find a generator, you might call it, for a given ideal that might be described in some other way, you've got to find a polynomial, a non-zero polynomial of minimum degree in that, in I. And then this will be true. I, for example, might be described as, say, all polynomials in f of x that, say, have 0 as a root. That might be the way I is described. Set of all polynomials in fx such that f of 0 equals 0. If you graphed the polynomial, the origin would be a root, a 0. Since this is a principal ideal domain, I should be able to write this as, with this notation, for some generator. And the theorem is saying it's got to be a minimum degree in here. This can't contain any constant polynomials except 0. And I guess that's part of the reason, at least, we're defining the zero polynomial to have an undefined degree. The minimum degree polynomial that you can have is something to the first power x, and x is in here because, yeah, you plug 0 into x, into g of x equals x, you get 0. So x is one example, at least, of a polynomial of minimum degree in this ideal. And therefore, by the theorem we just looked at, this has got to be true. There could be other polynomials that could be used as generators, just like you do for cyclic groups. It's definitely not clear how this is all going to play out. We won't be able to see how it plays out until we actually play it out, until we actually go through the content in every way we can to see how it all comes together. Chapter 17 is supposed to be a highlight, but there are more highlights to come of our main application. Okay, have a good day.